Thanks, Tori. So let's redo those intros right quick. I'm Shane Caldwell, Principal Research Engineer. I'm mostly focused on LLM training and evaluation for offensive security tasks.
Yeah, and Nick Landers, co-founder, general wrangler of a very talented team. Does a lot of awesome stuff. We're gonna do a split presentation here. I'll take the first half, Shane will take the back half. We'll give you guys some context for what we're covering. In addition to us personally, I kind of want to talk about the problem set we focus on. We exist at this intersection. We built this conference because we care a ton about this space. I remember 2 years ago, Will and I talked about what it would be like when security people and machine learning engineers meet in a room. And this conference is really awesome. It's a great representation of that goal. So super grateful all of you guys are here. I hope this continues to grow. At Dreadnode, we handle a lot at this intersection. And at the end of the day, it all really relates to our core goal, which is to show that AI can perform these tasks, ideally exceeding human capability. And this is the goal that I think we should all set out to accomplish for many reasons. Some might be because we want to see machines hack machines, but at the end of the day, we're moving into a new space, and this technology is going to start to accelerate everything. Defense, offense, the interactions between them. So we need to get familiar with it. In terms of how it's going, what I love in the past year is we've seen a huge acceleration from can it do the thing to, well, now I want it to do that thing reliably and I want to do it at scale. We've seen lots of great presentations the last 2 days that have talked about this problem set. And when we move out of doing the thing, we effectively move into becoming closer to our ML peers. So machine learning is a process whereby we let data do the hard work for us. Once we know that something is feasible, and we scale it and we optimize it, and we build better and better capabilities, which yields exactly the models we love today. So the premise of this talk and what Shane and I want to communicate is that the process we're going to go through is more important than the tech. So as an individual contributor, as a domain expert, we've clearly proven that with that skill set, you can come into the space and build something actionable, something real. And I think Josh's keynote kicked off this really great perspective for the whole conference of what does it look like to move out of the crawl phase into the walk phase and ideally into the run phase. So there's a big process that we're going to be covering, and we're going to kind of slice it in half. But the process is whereby we take agents, or really any sort of non-deterministic tech component, we call them agents, which I'll get into. We pair them with models, which are inference engines, environments that they operate in. We take inputs and outputs, and we calculate metrics, and all of that goes into a box, and we parallelize it. And out of that comes data that we pipe through some sort of training or optimization process back into the system. And the interaction there is nuanced that we'll also cover. It can apply to the model, which I think is the traditional way we think about training. It can also just be a process whereby we optimize the component itself, the prompts it's using, the tools that it uses. It's that intuition that we have as security people when you're working on one of these systems and you built a POC and you're watching it do a thing and you're not quite sure it's doing it the way you want. And so your intuition is to go in and fiddle with it. You want to turn the knobs. And the argument that Shane and I want to make is that's actually a really good moment in time to rewire yourself and try to pull yourself out of this loop. It's not healthy for you to be there. All you're going to do is produce noise in the system. The system should be there stable enough for you to start putting it through this pipeline. So I'm going to cover in this first half kind of the inside of this core box. So we've spent a long time building these systems in many different forms. I love the process. And at their core, they're really nice when you get the right abstraction. And so I'm going to talk about kind of the tech side that helps facilitate the back half of the process, and Shane will take over for the training and the scaling and models and environments. So when I think about this little interior box, it's software, it's non-deterministic, it's an agent, it's whatever term you want to use. There's some criteria we really need that we care about a lot if it's going to fit into this pipeline. One of them is that we need to be able to evaluate very easily. I use the term trivial. The evaluation, the measurements we take of everything going on inside of that box should be very local. They should be modular. We shouldn't have to build the system and then think about measuring it after the fact. And those things should be wired up really nicely together. Because in order for our data to be useful, it has to have those measurements associated with it. I think structural consistency is a mapping from the machine learning space, where I see a lot of power in core algorithms or frameworks like PyTorch, where you can represent a neural network or many different variants of learning systems in common primitives, and you can build for lots of different use cases. And somebody who knows PyTorch, if Shane is in bioinformatics, or if he is doing image classification, can look at my model and roughly understand what it's doing. And there's a transferability there. So I'll get into what the tech looks like, but I want to sort of mirror that on these higher order systems like agents. And the last thing is scalability. The system needs to be able to plug into that parallelization on the back half. And this is nuanced. As an engineer, it's hard, because when you're writing code, it's really annoying to think about what happens when this code runs 100 different times. There's some tech that makes that easier, but at the end of the day, you should be effectively thinking about that as a pre-requirement. It's something that machine learning does. You're never going to find a model that doesn't take a batch of inputs. By nature, they're designed to be executed at scale. So I'm going to start by talking about what we maybe define as this box that we call an agent. Or if we have a box where there's agents inside, I've kind of color-coded here of like, you can imagine the green boxes as being the things that we associate with agentic work. So they're non-deterministic, and they're a little bit different than traditional software. But at the end of the day, they meet software somewhere, right? In order to make them actionable, we have to wire them up to like the rest of the stack. So if I just run inference and let a model think about all the things it wants to do in the world, but never actually carry those out, attach them to an environment, in an RL sense, then I haven't really done anything. It's not dangerous, it's not useful. And this wiring, while subtle and maybe you don't think about it very often, is actually super important. And so I'm going to kind of get into the details here. But I bring a software engineer's perspective. I love the space of engineering. So I want to kind of bring that framing to you and present the system like, what if we're an engineer coming into the ML space and maybe not necessarily the other way around? What if I think about agents as a piece of software first, as opposed to an algorithm or a way of describing a thinking machine? So the first thing I want to cover in a system like this is we have all these like little units that do work. And we call them tasks. They can be nodes in a graph. They can be lots of things. The abstraction is flexible enough, and all we really care about is there's a unit of work happening, there's data coming in, there's data flowing out, and there's measurement of that data. And what I like about this is we haven't determined that what's inside of this box is driven by a model. It could be a totally fixed bit of software code, like a tool call that we're engaging with the world in. Or it could be a very rich agentic system where there's an agent sort of computing a think react loop, and it's calculating tool calls and sort of building a compute graph dynamically. So we get this DAG architecture, which is a transition we moved through in, I think, agentic systems designs of like from very state machine systems to workflow defined systems to imperatively defined systems, which follows a lot of what we do in systems architecture or in software engineering. And if we just think of agents as being capable of plugging in anywhere in this box and they share the same pattern, they'll be reusable. We can turn each time one of those units is called into a line item in a data set, which is the power of the learning process we want to achieve later. In terms of evaluation, I covered it a little bit when I showed scores being attached to a task, but we mentioned this idea of evaluation being trivial. It should be imperative, define task local, and the frameworks can make this possible. If we think about scores as being something that we can just throw on any of these units, and we have a rich set of them, and they're kind of easy to click together, then we're almost defining the measurements we take, if you were to think a la PyTorch, where you're like computing metrics about the model's execution, right? It could be loss or a gradient, something we're backpropping against. We're producing a number. It's going to be attached to this node and that entry in our data set for the rest of time. Now, to get a little bit more practical, up until now, I've just been talking about software. And I mentioned that we can think about these boxes as carrying agents. I've laid out maybe a pattern here that's probably very familiar. Inside of this box, you're going to have some inference-driven system, and there's lots of different ways we might design this, but all of those are there to facilitate some sort of semi-structured way of letting the agent do work in our compute graph. And we're trying to balance the level of control we have over it and letting it explore enough to be useful. Like a React loop is really common. And in a software sense, that's we're effectively giving the agent some control over executing a repeated set of actions where maybe inside of there's like a case statement. We're saying like, if you want to use tool A, we call tool A and then return it to you. We control the number of times it loops internally. We refer to that as max steps. It's how many times we go back to the model. But what I like about this is you can talk about the interior of this box and its wiring, but you can also just think of it as a thing that's one of our tasks, and an agent receives input, produces outputs. In terms of lifecycle, a really nice implementation here that I think software engineering have had is if you think of exposing events out of that box, moments in time where you kind of get some control over the loop or the compute graph the agent is constructing or the inference engine is constructing, you can pair that with like a reaction system and you get this really nice flow where inside of the box, once you kick it off, it's just going to start emitting events of what's going on. And if you don't do anything, it will just run until some fixed life cycle has been established, usually a maximum number of steps, or maybe we define a stopping condition, like when we receive a message from the model that doesn't have any tool calls. We consider that like the return statement in our function. And these events, once you've established them, pair really nicely with scalable system architectures. So we can take these events and we can put them in like distribution event buses, where now the agents don't necessarily have to be local to the code that's manipulating them or monitoring their compute graph, taking scores, or making reactions based on that. And I think the last point I'll make here is, specifically in the eye of messages, I think the mature thinkers in the space are very aware that context is the most important thing, or very important thing about agents. And I like to draw an analogy between that and the care and maybe sort of soft rules that we put in place in software about like the interior of a function. When I write code in a function, there's a general rule of like that function shouldn't be doing too much. It shouldn't be too big. It shouldn't have like a lot of very custom logic. It should be modular and plugged together. And we can kind of think of this context, like I'll get into, as some analogy of what's going on inside of that function. Its behavior is defined by that context that we put into it. Observability is the back half of this software stack that lets us start to turn all of this data we're collecting into a trace, and to quote like a very core software engineering term, but maybe to Shane's point, more like a trajectory. And this trace can track, just like we do with traditional software, everything going on in this dynamic system. I love that people building agentic systems have naturally arrived at tracing. Traditionally, we used it to like monitor applications, their health, their uptime, to debug them. And now we're using tracing in this dynamic system to track the behavior of non-deterministic systems. So we just get all of this power for free. We can track spans, their relationships to each other. We can track their inputs and their outputs, their execution time, their health errors that occur inside of it. And so we can take this trace, which is an extremely rich piece of information, and use it as in any part of our training process. For the purposes of what Shane's going to talk about, usually it's taking some extraction of that full trace, which might include like very rich functions that were called, functions that called functions, and just flattening it into, I care about a stack of messages. Because ultimately that's what aligns with my training process. I need a set of structured chat logs that I can have scores assigned to them, and I'm gonna go put that into a pipeline and apply RL to them, or fine tuning. So you'll hear me maybe poorly use the terms a little interchangeably, and that's not correct. But when I talk about tracing, I'm just thinking about like telemetry systems. Trajectories are usually training specific, where they think about the traditional RL tracking an actor in a system. In terms of improvement, which is the last piece to our puzzle, we can think of these little dynamic boxes as maybe having like two core components. They have the context, which I mentioned earlier. So whatever you want to think in terms of the abstraction from function calls down to prompts, down to messages, down to tokens. At the end of the day, there's some tokens that arrive in an inference model. And we can kind of think of this as our control surface. And I think people context shift between these, no pun intended. But they are two different things that we can train or optimize against. So if we think about just training the model, we get into model selection or quantization, we're caring about modifying or manipulating the inference engine that's paired in this sort of plus formula. So like, what is this half of the influence to the function and its behavior? And there's lots of different great algorithms and training code for making this process better and learning from the data you're producing. Then on the other side, and there's a great line up here with like adversarial testing, we can think of the model as being sort of a fixed unit. It's a player in this unit of work. It affects the unit of work. If I use Claude 4.5 or GPT-5, those are going to produce different behaviors. But if we fix it, then we can start to look at optimizing a prompt, optimizing the tools that are presented to my agent. Anything that flows down into that context is just another piece of data that plays in this formula. So like JEPA or MyPro or GEPA, or it's kind of the GIF thing, are ways that we can optimize this half of the equation. And it's super popular in AI red teaming where we do adversarial examples for jailbreaking. We effectively optimize a prompt just like we would for gaining performance, except our measurement is a little different on the back half. And in addition to context, and an important point that I think makes a lot of power in these frameworks, if you are modifying context and you have these big objects in code that have some downstream impact on context, they could be the instructions which are placed in the prompt or the messages, could be the tools that you have available, or things that you're doing like hooks where you're tuning that control graph. Those, if we can surface them, become like hyperparameters, and we can apply the same lessons we learned from Optuna and traditional machine learning algorithms or libraries, and get a system where we can treat this whole dynamic software stack as a rich box that can produce data, and we can learn and inject those lessons based on some goal, reward, verifier back into the system, and hopefully optimize. So I'll leave on this idea, at least in terms of slides, that the holy trinity of ML ops that we're trying to build up, well, these systems that I've just talked about, are all about the infrastructure we use to deploy the workloads, the observability we use to capture the data, and the back half of the improvement process, where we're training models or we're just optimizing some portion of the agent itself. I apologize for the size here. We're going to work together to try and see this. So this is a bit of a strange insertion, but I'm going to start talking about what these systems look like in practice. A lot of this is going to be prep for what Shane's going to talk about. So we're going to do kind of a mid-presentation demo, because sometimes I find that the build-up into a demo at the end is like laborious. And so we're going to jump into some agent use cases and talk about what this sort of system creates for us in terms of flow and process. So I'll start with Game of Active Directory, Go environment. It's a really common training environment for people who want to learn network ops. So for those in the room who aren't familiar, think of this as like a training environment for people who want to run malware or compromise Active Directory networks. It offers a really great place for us to start testing and validating this data flywheel that we want to produce and gathering, I guess, trajectories or useful information about agents. So now I'll figure out how to change tabs.
Live.
So this network ops project I have open right here is a reflection of all of these data collection systems we've been having going on. So we have an agent. It's defined really trivial in code. It has a bunch of scores and verifiers attached to it. It's actually a really basic loop in function. And I'll note that that's kind of important. Once again, removing yourself from the decision-making process as quickly as possible is the goal. So it's really easy to get into the nuances of like, should this be a swarm system or a multi-agent system, or how should this layout occur? Like, what code do I have to write? And you can kind of just get something working and then immediately move to the back half. It's actually better that way. You probably should not be making core decisions about how things work, because you should let sort of map through that work for you. So we have some, can you get that mic for me? All right. We have some runs that are being produced, and these runs come from individual attempts at compromising this network with various models. So at the top level, we get these a bit like an experiment tracker, right? These are agent specific, but they work just like weights and biases or MLflow. And when we look at the charting, we can get some idea of like performance characteristics. So this is where that verifier step is super critical. Building that in early lets you get to this step where you're starting to ask questions about how do I improve the performance of the system, and you can answer them immediately. So we have these like great, I love these bars, they look really fun. So we have this kind of broad score that's some composite of like how many domains and how many users have you compromised. And we can get like wall clock time, and we can get stepwise comparisons. And it's very hard to see, but we have here like GPT-4.1 popping the first domain in this network totally autonomously from 0 access in like 2 minutes, something like that. Which is pretty wild, right? This is the step where I think a lot of people would be really excited about. Oh, I built an agent that does a great thing. And because we have this observability system, I can crack open a run. I'll pick one here where a domain was compromised. And we get this introspection phase where we can start to see all of the rich data that trace has produced for us. So this is stuff Shane really loves. He specifically gets really excited about jumping into an agent and viewing the message log. To him, that's the important part. That's the trajectory that he's going to train off of. But it's not just constrained to the message log. We also get rich metrics about lots of things that happened in the system. The number of tool calls that were made, what was the success rate of the tool calls. Any sort of metric that we care about adding, we can put in here and start to impart knowledge. There's a secondary phase to this, which is after you have this great gathering data step, and you've learned, which I'm going to jump ahead a little bit past Shane, you want to start packaging them up. So we want to turn them into capabilities. That's what we care about in terms of final results. And so we can take these agents that have now gone through this pipeline and put them into a distribution, just like we do with models or anything else. I'll see if I can kick off a .NET reversing one right now. The important part here is we've gone through the hard step, and there's like back-end scaling that backs this whole process. So I'll do OAIC.
Yeah, hold the mic for you. Teamwork makes the dream work.
What's funny is I have a mic on this side, but I'm not using it. My screen brightness? Okay. Nope, you're all good. Apologies for the view. I'll skip over try to get to a view that has a little bit more visual details here. Yeah, I guess, okay. If you guys want to see me click a button, we can click a button.
Let's see him hit the button, folks!
All right, so here I'm kicking off an agent. Will's in the back. He put this agent together, and he has been hitting up and enter on this agent for a really long time and is super happy it's in a cluster now. So he doesn't have to do that. But we can drop in a bunch of packages. .NET reversing agent has gone through this pipeline. We've collected data and established some confidence in its behavior. Shane is going to talk a little bit about different scaling mechs. We really like Ray for this. So to kind of get practical about the element of your agent needs to be scalable, it needs to work in its tool setup and everything to be plugged into a big cluster. We have effectively jobs in the back end that are deploying this agent across all of these binaries in parallel. These are effectively pulling down assemblies, reversing them, gathering data for us. This process is there to like help move us away from manually writing a script that's going to do like a for loop and create agents for us. So it's a little bit difficult for me to see. But, we can jump into like an individual job, see its status. Ray is going to collect a bunch of additional information for us. But most importantly, despite the fact that we're using Ray for the distribution, the runs themselves all flow back into the same platform. So because we built our code around gathering data one way, we did our experimentation in one phase, we do deployment in another phase, and all of that information flows into the same space. And we could get stacks of all of the assemblies that are being processed. I think Shane will throw out some stats, but Will is like 150,000 assemblies in or something like that. It's extremely cool. And regardless of what agent we're building, for whatever use case, this pipeline stays stable, and we can carry through in this process, build improvements, deploy modular agents or any agentic system, and get performance out of them. So I'm sure I'm behind. I've probably taken a lot from Shane at the moment.
No,
so
it's all good.
I'm going to hand it off to him to talk about RO.
Yeah, you're great.
Excellent. Martin says I'm good, so
I said you're great.
we are good.
I feel better than good.
Perfect.
Look at that.
How's that?
Mission impossible.
Thank you, Kate. Appreciate it. Okay. All right, so I'm going to hand it off to Shane here, save my voice, but Shane's not going to talk about the other half of the process, which I teased a little bit.
Thanks, sir. How about that landers, folks? All right, so Nick just broke out a very important but very complicated set of structures that you have to worry about if you want to deploy agents. And the fact that you have this large collection of linear algebra, but the rubber is going to meet the road when it actually runs on like hardware. I'm a math person, so I don't want to deal with all that stuff, but having a platform that collects that data for me and lets me go through the process really abstracts that and lets me do what I care about, which is what we're going to talk about now. So let's talk about training. We want to go from a proof of concept harness to something we would consider state of the art. This used to be super common as short as 7 years ago when you were doing something like computer vision. Essentially anything you train to be state of the art, and it is only very recently we have seeded that to labs that we take the best model they give us and sort of plug it in. But if you want to get back to that process, let's talk about how we can do that. So it all starts with environments. You need an environment to build a proof of concept. If you look at like Do Shop or Go here, I'm pretty sure like 60% of this room has wired up a demo attacking one of those targets. And there's a good reason for that. It's because those are task-rich environments. And there's something to say about whether those environments are in the training data, but whether they're in the training data or not, models do not trivially solve them. So until those benchmarks are saturated, those benchmarks are free, and you should use them. So those ends they're going to get you started, but they're not what we would call in distribution. Right? There are a lot of things about those that, while they're not saturated yet, when they are, we wouldn't say that, okay, we're ready to go to production, right? We want ends that are in distribution for us. So one way you can go about this is finding environments. So for example, if you're interested in code scanning, you're in a really good way because you can permissionlessly go to github.com and find more code than you could ever need and scan it to your heart's content. Same is true of Docker Hub. If you're interested in web apps, obviously bug bounty platforms are like the testing distribution, right? If you can make it in a platform where apps have already been tested by a variety of hackers, then you can kind of make it in any 5-day contract pen test you might be interested in doing. So we would expect for those parts of our field where you can permissionlessly access those ranges that the capability development would be faster. And I think if you look at the last year, that's been true. And if you can't find your environments, you're going to have to build them, which is exquisitely painful but necessary. So you talk about like what Go provides, that realistic training environment, that took like individual people a long time to do. And to replicate that or go past it is going to take a lot of investment in engineering. But it's sort of a requirement for actually having benchmarks to know like what are we doing and how well are we doing. Our goal here, this is like, Josh pointed this out yesterday, and I thought it was really great. He's kind of talking about the benchmark crisis in offensive security. And I've seen a lot of noise on Discord today about just that, which I love. Our goal is to get to something we would consider statistically significant as a benchmark size. Like the point of a benchmark is not necessarily to show that my model is better than your model. It's a hill to climb, right? You want a number that is representative that you can push upwards. And to do that, you need to get to like a certain density of tasks such that you achieve statistical significance. So if we look over at the sort of our successful older brother software engineering agents, we can see that their benchmarks, they're in like the 500 to 225 task range. If you were to look at like how many vulnerabilities exist in Go or Do Shop, that's on the order of like 50, 60, right? So we're about an order of magnitude off, which isn't ideal, but an order of magnitude is tractable. And maybe the second most important thing about getting to that like sheer density of tasks is it forces you to invest in infrastructure to run those tasks regularly. It's really easy to just run evals on your laptop. And I would say onto you, if you have a sufficiently large benchmark, you're going to run your evals very infrequently because it's a giant pain. The evals have to be large enough to be statistically significant, but fast enough that you can run them in your like experiment loop and get useful feedback from them. And to do that, you just sort of naturally end up leaning into like horizontal scaling and infrastructure. So for us, that's rare. And that infrastructure that allows you to scale your evals is the exact same infrastructure that's going to allow you to scale your agent anyway, so you might as well just go through the engineering effort. One thing that's been super interesting as we go through a bunch of different use cases at Dreadnode is the selection of tools. Sort of naively, you think like, okay, I'm gonna go for tools that I expect to be represented in the training data set. And what you find is those tools aren't necessarily the ones that can stand up to the throughput of an LLM. So we've worked with a lot of software, a lot of great software we love, like Mythic and Sliver, that while great pieces of software, once we plug them into agent loops, things like the number of concurrent calls we were making or the size of the data that would land in a C2 after 100,000 agent runs was just really starting to chug. And we found that the tools we end up reaching for are tools that were already designed around automation in mind. The human was already out of the loop. And those tend to be more scalable, multiplayer, et cetera. So now you have this system that lets you generate a lot of data, which is useful. But if you can't go through that data sort of automatically, then the triaging is all on you, and you actually haven't saved yourself very much work at all. So your goal is to get to something empirical as fast as possible. So you want to pull yourself out of the loop of like, I'm going to tweak this doc string, I'm going to run it, and ooh, that's smarter. You want to get to a place where you're surfacing like numerical information that you're using to make those decisions. And the major way to do that is with verification. So evals, like the evals that are recorded in like system cards, for example, they all have a sort of verifier attached to them by default. So if I'm looking at a mathematics eval, I'll give the model a word problem, and the answer is sort of linked to that word problem. And my job is just to run a regular expression, see what the model gave me, do an equal comparison in Python, thumbs up or thumbs down. I think the equivalent for information security is probably like a CTF, for example. So we have a canary string that's sort of loaded with this challenge, and we assume that if a model brings me this like random string of letters and numbers, it probably got that by succeeding in the challenge, so that's like a good sign. Those verifiers are great for environments that you control, right? But they assume that you already know the answer. And the thing about reality is that you don't know the answer beforehand. That's why you wanted to do this in the first place. To do that, you need, so if you can think of like the eval verifiers where you're taking information that you already know about the system and you're waiting to see if you get that answer, I would call that a brittle verifier because it's very specific to the particular task you're evaluating. What we're sort of looking for is a generic verifier. So it's something you can take at test time when you don't know the answer and get some signal of success, right? So for example, if you were working on web application testing and you have an alert box pop up, if you were trying to do cross-site scripting, it's a pretty good sign you succeeded. Or if you were working on lateral movement, for example, and you're sampling runs from the agent, and then you see a beacon open up from the machine that you intended to. That is an external signal outside of the system that is giving you information about task success, sort of regardless of whether you own that infrastructure or not. So what that allows you to do, sort of most crucially, is just separate the wheat from the chaff at scale, right? The important thing is to be able to run this model at a large scale, like more than a human being could do on a laptop. And if you can make sort of a distinguishing understanding between your success and your failure, you're sort of at what we would call minimally successful. We've got a lot of examples of this flow at Dreadnode from a lot of members of the team. And we found it is a recipe that remains true throughout all information security domains. For example, this work was presented at LabsCon by one of our team members. This was like autonomous CTI research. And given a series of leaked data sets, we found more interesting data points than Bellingcat. If you're interested, talk to Martin. The .NET reversing agent is probably our largest scale example to date. You're looking at a source of like, you have, 100 million packages on NuGet, and you're running this process on all of them, just like slowly chunking through them. You have some verification function that determines whether you found something interesting through that process, and you surface those for like triage. So like from a numbers perspective, so far we've chunked through about 150,000 of those, and maybe 10% of them were worth triaging, and then 50% of that was like something valid. Even at that scale, to be able to just do that like away from your laptop, you're already like generating value, right? You're doing the thing successfully. So this would be like an example. This is an architecture diagram of our reversing agent. And you can sort of see like how the data flows and where the verification steps are that are going to determine whether you've been successful or not. And then the platform that Nick created, I was like, where's Nick? That's surfacing all that information. So when a data scientist gets around to looking at it, he has something to sort of cling on to. Okay, so we might assume that that whole process up till now has been with some, you picked a off-the-shelf environment, you picked an off-the-shelf model, but maybe you want to make the weights sort of yours so you can actually start optimizing, right, directly for the offensive security task. So you've got this scaled agent, it's generating a bunch of data, and you know which data is good and which data is bad because you're verifying. That is basically rejection sampling for free on a massive scale. So you start to see where you could get data that would be worth, doing supervised fine-tuning with. So your next question is, okay, I need to distill from something. What models are worth distilling from? This also assumes that you care about licenses. But we do. And we would say that open models are becoming competitive, right? I think this year in particular, Kimi K2, in an eval we published called Pentest Judge, we found it was performant with a lot of the frontier models. It was actually quite competitive and quite cost effective. So we would think of that as like, due to its ability to do like prolonged tool calling over a long time horizon, that's sort of useful behavior we would like to extract. And it has a fairly permissive license. In terms of what you're going to distill into, you got a lot of options. There's a new model coming out, according to Twitter, every like 6 hours. And that is at any size you could imagine. You want a mixture of expert, you can have that. You want a dense model, you can have that. You want 20 billion, 4 billion, it's all available. And I would say that like a lot of people believe that open models are sort of incapable and not worth fine-tuning because you'll see them in an eval and they'll be like, oh, I got like 1%. And the amount of tuning you would need to do to get it to actually participate in the harness and then see that score like massively shoot up is very, very low. So I would say open models are like underhyped at the moment. So you decide to train. How are you going to do that? You don't need a cluster necessarily. So like LoRa, for example, gives you an adapter, which is a very small amount of learnable parameters that you can do training on. And while having a very small number of learnable parameters, they nevertheless have a large upstream effect on model performance. So this makes it sort of tractable to train models around the 4 billion to 8 billion size on a single like H100 node. And it's never been easier to get a single H100 node. There are a bunch of compute providers like Lambda, Prime Intellect, Modal. Modal's got some really confusions actually. That let you spin up a node for a very brief period of time to run a training job for 8 hours a day, 2 days, and spit it down. So you don't necessarily need like a long-term contract in order to get your toes wet with model training. So now you've got this data and you want to start tuning your smaller model. Supervised fine-tuning requires what I would call very lightly scaled data. So I feel silly saying scaling here because if you look at like a pre-training data set, you're talking about like 13 trillion tokens or something like that. You don't need anything near that size. Your mileage may vary depending on your sort of task complexity, but I found these numbers are sort of useful. If you've got about 100 trajectories to fine-tune on, you can expect that that open model is now going to play well with your tool harness. So you expect it to at least participate in making sort of contiguous tool calls for your task. Around the 5,000 mark is when you start seeing like partial success. So if you're willing to sample long enough, you'll start to see the agent will occasionally do the correct thing that you want it to do. Over 15,000, that's when, for me, I stopped really seeing improvements in the LoRa. The LoRa sort of converges. That's our LoRa. That's when you converge. Once your model sometimes succeeds, so around the 5,000 part, you're ready for RL, right? It's sort of a post-training step. So those verifiers that you develop to scale the amount of data you have now play double duty as reward functions. So you sort of take what is a Boolean, turn it into a float, true is 1, false is 0, and now you have like a basic reward function that you could take for training. The way that works, like what I would say the API of the learning signal, the contract you have to commit to, is you have to be willing to take a task and sample multiple trajectories from the model, so multiple attempts of every task you're performing. You need to be able to grade those, and those grades have to be meaningfully different. So all of the gradients are going to be informed by group level statistics over those rollouts. So those rollout values have to be different. LoRa also behaves super nicely with RL. This was some research that Thinking Machines put out literally last week. Excellent timing. And what they showed essentially is that even for very low rank adapters, which is to say an even smaller number of learnable parameters, the convergence points for training with GRPO ended up being very similar, which is to say just additional compute savings for you. Frankly, the weights won't be the problem. The activations will be the problem. So to get the most out of RL, we talked about the first failure mode, which is I'm sampling from my model over and over and over again, and I'm not succeeding. What should I do about that? I would say you can either pick easier tasks, or you can do more supervised fine-tuning. I would go with the second one, because you've already built the system to collect data, right? The other failure mode is you succeed all the time, right? As soon as all those trajectories are getting that same success signal, you no longer have anywhere to learn from. The solution to that is to sort of make your reward function more dense. So we described a binary success or failure. You talked about this yesterday. You can express preference over your trajectories in a variety of ways. So ways you might do that is to say, I'm looking at the specific tool calls within my trajectory, and I would prefer they use some tools over others, and I could sort of tweak the reward for that. Lower tool count is one that's sort of very general. So you can imagine if I have 4 trajectories that have varying numbers of tool calls, I would prefer the model that could solve it in 15 compared to 60, or a less think token count. There you go. Because it just takes a lot of context. So that essentially gives you a more varied reward function that you can learn off of longer. I will say when you start compounding your reward functions, you're sort of introducing secondary objectives that the model can sort of hack around. The most well-published example of this, I think, is when DeepSeek did its training, they were sort of rewarding for additional think tokens. And for a certain time during that training, it's sort of improving your math scores. And then eventually you're just reward hacking and adding think tokens for the love of the game. And now we have to clean it out of our context windows for the rest of our lives. So choose your reward functions carefully. So we're talking about the ability to express preferences over trajectories and doing that through verifiers and reward functions. I think there are a lot of cases in security where you can imagine not really knowing how to write a generic verifier. That's why it's very difficult. If there's a single high ROI activity, Nick and I are talking about taking yourself out of the loop as much as possible, leading it to optimization. If there's one place it is actually valuable to get in the loop, it is finding those generic verifiers that are specific to whatever domain you spent your entire life studying. But you can imagine the world that leads us in is one with very spiky performance, right? This is a world where, due to the external signal of the alert box popping up when I pop cross-site scripting, I can now train models that are very good at that. They're not good at either, right? So you get this very strange, spiky outcome that is sort of related to where you can service those verifiers. We would sort of prefer if we could instead express those with natural language. So a good outcome would be if instead of worrying exclusively about where you could get a generic verifier for, or whether you could express your preference with a Python function, you could instead express it in natural language and leave an LLM to judge it. And that goes beyond things just like the difference between an IDOR versus a cross-site scripting. You could think of to get these agents into production, I would want models that were trained on specific goals, but also followed specific guidelines and specific restraints. You can imagine when I was a pen tester, I had a specific goal to compromise a network, but I also had uptime constraints and scope. And if I violated those because I was optimizing for one thing, then I would be fired and my professional liability insurance would be upset. So when you talk about having a judge, there are a few ways you can imagine doing this. You can imagine doing it as a verification step. So for example, if you have a web agent and you say, hey, I want you to log into this thing, and then the agent attempts that and believes it's done it. There's sort of a hard world where you imagine, how would I write a Python function for that? So like, okay, I'm gonna look at all the cookies at time step 1 and time step 2. I'm gonna figure out if they look like cookies that mean I'm logged in, or you can just take a screenshot and pass that to the judge. The question you're actually asking is just, hey, do I look like I'm logged in now? And that's a question you would expect any human being with sort of a basic semantic understanding of image data to be like, that's a profile tab, you look like you're logged in. So that's like a very easy use case for a judge. Something slightly more challenging is if you want process level control, you care about not just the outcome, but how it arrived at it. You might want to take the trajectory in its entirety and pass that off to a judge, and then let it determine whether it succeeded at the sort of task you were interested in. Now, this is obviously, in principle, possible. You can definitely write code to do that. The question would just be, okay, when the model gives me that structured return judgment back, is it useful or is it accurate? So we looked at that specifically for network pen testing. So the same agent that you saw Nick pull up a few minutes ago, we generated 30, 50 runs of that, and we had a series of different tasks we wanted out of the model for those runs. So those are mostly things like operational security constraints or tradecraft things like, hey, don't brute force, hey, do stealthy things. And we had the judge grade all those trajectories for all of those different tasks. And then we compared those judgments to a domain expert who judged those same trajectories. And then our goal was essentially to determine, okay, how often does the domain expert and the model agree? And what we found was pretty frequently, over 80% of the time, which is way, way, way above random. And we found it was also pretty cheap. So for judging a 60 to 100 trajectory tool call, we could process that all with the model and get a score that's like 80% accurate for like $1. So that sort of tells you where the research is going in terms of like, after this period of spiky generic verifiers, we're going to get to a period where we're sort of doing that expression of natural language judge post-training. So you've established a loop. You've distilled, you've done supervised fine-tuning, you've done GRPO, and all that's left is hill climbing, right? Why did we bother to go through this entire process? We did it so we can meaningfully improve on benchmarks, right? So this is like a very simple example of goto enumeration where we saw that like 01 was successful at this sort of enumeration task 60% of the time, and just going through the process we just described to you, we're able to get to sort of 70% with an 8 billion parameter fine-tune. And that's not like 100%, but that is the hill that you can now then begin to climb. One thing I would say for those of you who are sort of taking your first steps into model training is that models age very quickly. So you gotta sort of be ready to throw the weights away at a moment's notice, like what's the heat quote?
I don't know.
That's a quote. When the heat comes around the corner, you gotta walk away. Thank you. There you go.
There we go. There we go.
Can I get a little applause for that guy? All right, we're watching Heat later. So models age fast. You gotta be ready to throw the weights away at a moment's notice. And that is sort of intimidating because you imagine the infrastructure that is like sort of it takes to do this training and how much it costs to like spin up those H100 nodes. What I would say is if you're looking for sort of like permission, granted, but if you need like permission you could present to a boss, you can look at sort of the differential between how much you're paying for the APIs to do these things today and how much it costs for like the electricity to run it on an A100. All that money you're saving can go back into your R&D.
All right, we are boxed up here. I think I'll maybe do a pass on these last thoughts and see if Shane has something. I want to recap our broad goals. You've seen a lot of narratives come through in this presentation. Shane and I both really agree that pulling humans out of the loop is our P1. It's we influence the system too much. It's not going to be the thing that scales. We aren't going to be the ones who solve these really nuanced problems in these systems. This is a lesson that's been learned in so many domains before us. So it's really hard. And I actually sympathize a lot because I'm a security person. And for all of my career up until now, I've been rewarded for getting really detailed about technicalities. right? It's like if I understand the system better than the next guy, I can do the coolest exploit or hack the best box. And so there's this feeling you have, and I feel like everybody who's ever played with these systems knows exactly what this is. When you build the system for the first time and you're watching it go, and it doesn't quite do the thing you want. It maybe veers, or it doesn't finish quite right, or it bails early, and your first intuition is, oh, I'm gonna go like edit it. I'm gonna like figure out what's wrong with it. My argument is that's exactly the moment in time you should start pivoting to writing verifiers and getting yourself out of the loop. You've got a system that can produce varied trajectories. We now just need to score them and put them into the process. I think the other half of that, kind of the implication, is domain expertise is extremely valuable, and there's a lot of very talented people in this room that could build systems that are capable. But at the end of the day, the process is going to win out. And I think Josh made a great point in his keynote where he warned about the idea that you can build a very complex and brittle and tuned system, and it's going to get eaten. It's going to get eaten because there are people solving really hard problems at the very big scale, and they don't care about the small nuance. They're just going to let this process take over for them. And lastly, if you didn't get it from Shane and I hate writing verifiers as much as the next guy, making that easier, making it easier to write and easier to express, building that into frameworks, building those into our tools, and then making that part of our workflow is going to be a really critical part to seeing better monitoring when we put the stuff into production, better shiny rocks, to Will's point. He loves a flag that he found credentials, and also this post-training process, and anything that has to do with optimization. So those verifiers are very critical. It's kind of a net new skill. It's a muscle for me to exercise as a security individual because that hasn't traditionally been how I work. So anything from you?
Only one thing.
We're watching Heat.
We're watching Heat tonight. If there's anything I want from this conference, when we all come back here next year, you're the people who can make sure we never have to talk about Goad ever again. But that won't happen until it's a saturated benchmark. So go out there and build some verifiers.
Thank you all. Appreciate it.
Thanks, guys.